We've been talking about equilibria and the equilibrium constants. And today we're going to talk about something called the equilibrium quotient. And this helps us to predict which direction the reaction is going to go in, given a particular amount of reactants and products. So the reaction quotient, which can be QC or QP, just like the equilibrium constant can be KP or KC, is calculated in the same way as the equilibrium constant. So in a way, they are the same thing. The difference is that the quotient is calculated when it's not at equilibrium. So the reaction doesn't have to be at equilibrium. So we're going to calculate this reaction quotient using the current concentrations. And then comparing Q and K will tell us, is this reaction going to go in the forward direction or in the reverse direction? So for this generic equation, QC would be the concentrations raised to their powers, etc., just like K. When the reaction is at equilibrium, then Q is equal to K. So Q is calculated exactly like K, it's just it may not be at equilibrium right now. That was scary, another thing flashing up. Okay, so let's try to make sense out of this guy on a Monday morning. So on the y-axis we have a scale of 0 to 1.5, 3.5. And this is going to be either Q or K. On the x-axis, we have concentration. Here we've got reactant A forming product B. So at the beginning, we start out with only A and no B. We've just got the reactant and no product. As the reaction progresses, then it will go to products and we'll have less reactants, right? So here, if we calculate Q is going to be equal to the product concentration divided by the reactant concentration. Well, the product concentration is going to be 0. So Q is going to be 0 here. As the reaction progresses, the concentration of product gets larger and the concentration of reactant gets smaller. And so the value for Q is going to get larger. When we get to the point where Q is equal to the equilibrium constant, we are at equilibrium. If we push the reaction further to the right, if we have more products, now the concentration of products divided by the concentration of reactants is a larger number than K, and this tells us that the reaction is going to move to the left, back towards the reactants. It's going to go to equilibrium. So if Q is less than K, the reaction is going to go forward. If Q is greater than K, the reaction is going to go in the reverse direction. It's going to go to equilibrium. Okay, questions? This is one of those topics that is very hard to explain, and it's kind of hard to understand. Once you see it, it makes sense, but getting to that point can be a little bit challenging. Any questions? Oops. So the reaction quotient in relation to the equilibrium constant is a measure of the progress of the reaction towards equilibrium. If Q is less than K, that means it's approaching equilibrium in the forward direction, it's making more products, and it's going to keep doing that until Q is equal to K. If Q happens to be larger than K, and how could that happen? Well, if we have this reaction vessel and we just put product into it without any reactants, right? It can't go in the forward reaction, there's no reactants to react, but it can go in the reverse direction. So when Q is greater than K, the reaction is going to proceed to the left towards the reactants. Again, it's trying to get to that equilibrium place. When Q is equal to K, the reaction is at equilibrium. So at any given temperature, the equilibrium constant is a constant. It has one value. Q is not a constant, it's a quotient, and can have many, many values. It depends on the current state of the reaction, the current concentrations of reactants and products, and it will change as the reaction progresses. Any questions? It kind of makes it simple that we calculate it in exactly the same way, but then it kind of makes it complicated too, because then it's easy to get them confused in our minds and try, it's hard to remember, well, what exactly was the difference between Q and K? Q is calculated at any given time, at any given concentrations. K is at equilibrium. Okay, consider this reaction and its equilibrium constant. A reaction mixture contains NO2 at 0.0255 molar and N2O4 at 0.0331 molar. Calculate QC and determine the direction in which the reaction will proceed. So we're going to calculate QC using the same type of expression that we use to calculate K. So here we have gases, and we've got product and reactants. We don't have any liquids or solids, so we don't have to worry about those. So we're going to have the product concentration, NO2, and that's going to be squared because its coefficient is 2. And that's going to be divided by the reactant concentration. Okay? We're given these concentrations. This is at its current state, and we can plug these in and find out what the value of the reaction quotient is. So NO2 is 0.0255, that'll be squared. And 2O4, 0.0331. And then we do the math. And we get 1.96 times 10 to the minus 2. So we accomplished our first goal, calculate QC. The second one is more important. Determine the direction in which the reaction will proceed. Is this reaction going to form more products, or is it going to go in reverse and form more reactants? And we can figure that out by comparing this value to the equilibrium constant. So we want to know, is Q greater than or less than Kc? Greater than. When numbers are in scientific notation, it can kind of get a little confusing at times, because when there's negatives, the bigger negative is the smaller number. You can always write them out in decimal form if that helps. Okay, so currently we have this value of Q given by these concentrations. The reaction is going to move so that QC becomes closer to Kc, and it eventually will get there. Oh, Mr. Balo in the morning. Sorry, I'm not that entertaining. If this needs to get smaller, should the numerator get bigger or smaller? It needs to get smaller. If we want this number to be smaller, the numerator has to get smaller and the denominator has to get bigger. Does that make sense? So is that going to happen if we go in the forward direction or the reverse direction? The reverse direction. So when we go in the reverse direction, then the products are getting smaller, right? And the reactants are getting bigger. And so this then is going to go closer to K. So this will proceed in the reverse direction. Any questions? Predicting the direction of a reaction is actually a really practical kind of thing that can be done understanding equilibrium. You may be manufacturing something or looking at a biological process and you want to know, well, which direction is this reaction actually going in? Okay, so conceptual question. For the reaction N2O4 to NO2, same thing. A reaction mixture at a certain temperature. Why does it say certain temperature? Because it has to be at a given temperature. Do we need to know what the temperature is? No. So here they just didn't bother to get creative and tell us what the temperature was. They're just like, okay, the temperature is this number. So it initially contains both N2O4 and NO2 in their standard states, which means that the partial pressure of each of them is 1 atmosphere. And if you don't remember what standard states are, that's back in chapter 7. So if the pressure equilibrium constant is 0.15, which statement is true of the reaction mixture before anything happens? Does Q equal K? Is Q less than K? Or is Q greater than K? Well, we have to think about, well, what is K? What is Q? So this is for the pressures, right? So Q is going to be the pressure of the product squared divided by the pressure of the reactant. And it says that they are both 1 atmosphere. So we got 1 squared over 1, so that's just equal to 1, right? So is QP greater than or less than or equal to KP? It's greater than, right? Because QP is 1 and KP is 0.15. So Q is greater than K, which tells us the reaction is going to go to the left in the reverse direction. It's going to go this way. Oops. Let's do this one. It's going to go that way. Because this number needs to get smaller. So the partial pressure of the product has to get smaller, the partial pressure of the reactant has to get larger. And it will continue that way until QP is equal to KP, and then we'll be at equilibrium. In which case there's still reaction occurring, but in the forward and reverse directions at the same rates. Any questions?